What I'm going to talk about is work that we're doing in my group in simulating the properties of materials, specifically optical properties. And we're really interested in looking at how the complexity associated with the chemical structure, with the electronic structure, results in macroscopic properties that we can then measure. So before I tell you about the projects, just to motivate, what our interests are. So kind of in the broader sense, we're interested in next generation electronics. So we want to have new materials that can outperform possibly silicon or standard 3-5 semiconductors or bring new functionality. So for example, if we want quantum emitters, we may want materials where the quantum mechanical properties dominate. And so one area that we're interested in are low-dimensional and nanostructures materials. So there's a lot of potential in these types of materials for electronics and optoelectronics, but there are drawbacks in terms of having synthesis, having reproducible data, understanding how the quantum mechanical properties give us the device properties that we're interested in. So first principles modeling can help to address some of those challenges because, to make a material, to design and synthesize it, it takes a lot of effort. It's difficult, it's expensive, and time-consuming. In theoretical simulation, we could swap out bonds and swap out atoms and so on. And because it's first principles, we can have a sort of realistic understanding of how that material behaves if we make our approximations appropriately, so that we can then go to experimentalists, go to those who make materials and say, here are some materials we can try to make and incorporate into devices. In addition, experimental characterization is probing, in general, the macroscopic properties, or if microscopic properties can be probed, they're usually correlated. So like a phonon and a spin and electrons are all correlated, and so it's hard to tease out the different phenomena. In simulation, we can sort of incorporate each phenomenon separately, and so we can try and understand how everything sort of comes together and gives us an emergent property. So we use computation to speed up material discovery by extracting parameters, screening databases of materials for desired properties, predicting new materials. What I'm going to talk to you about today is really on the first point there, where we want to extract exact, maybe too strong of a word, but really accurate macroscopic optical parameters without empirical fitting, so that we can sort of give guidance to experiments, and also we can understand the underlying physical mechanisms behind optical properties of materials. So just another way to illustrate that, so if we start with the atomic scale, and we have these little nanostructures with their own response, we want to build an equation of motion as shown here. This equation of motion tells us how electrons respond to an electric field or an electromagnetic field. And from there, we can build a polarizability that you would measure macroscopically. If phonons come into play, then we can incorporate how that polarizability is impacted by atomic motion. And so that's kind of the idea. Sorry, I think there's a chat. Are all white? Oh.
Perfect, thank you.
Oh,
Is that okay? All right. Yeah.
Okay, so that's kind of our motivation, and I'm going to tell you about two projects that are really focused on time-dependent optical response in what I'll call quantum materials, because the quantum properties are important. So in the first, I'm going to talk about how we can excite phase change in materials using photons, using a Raman coupling. And in the second, I'll talk about spin-coupled exciton dynamics in magnetic materials. So before I get there, though, I want to tell you a little bit more detail about the computational methods. Just here's a cartoon. We start with the laws of quantum mechanics. We have some atomic and chemical structure. We put that into our computer. Our software gives us appropriate properties like light matter interactions, electronic excitations. So this looks pretty straightforward, but it's very complicated. So I'm going to spend a couple of slides telling you why it's complicated when we want to go from first principles. So we don't want to make approximations, but we want to have a quantum mechanical description of electrons. So here's the many electron Schrödinger equation. So that's what we need to solve in order to describe the electronic properties of a material. Most of our materials have a lot of electrons, and all of these electrons interact with each other. So here we have the kinetic energy of electrons, electron nuclei interaction, and electron-electron terms. And here I'm not even accounting for phonons or atomic motion. So we're within the Born-Oppenheimer approximation. So as you can see, we have to keep track of the position of every electron and how it interacts with every other electron in the system. And this is a correlated system. So all electrons are interacting through the Coulomb interaction. And so this is really difficult to describe, and it's pretty impossible to describe for real materials. So it's an n factorial problem where n is the number of electrons. And so we make approximations for the electron-electron interaction to make it feasible. And one approximation that's quite popular that you may have heard of is density functional theory. So in this approximation, we take our interacting electron system and we project it into a single electron, so a series of single electrons in an effective potential. And now we go from a n factorial scaling to a 3n scaling. And so we can study real materials with lots and lots of electrons. And this has been so powerful, and we've been able to do so much with it that Walter Kohn received the Nobel Prize for deriving these equations and discovering density functional theory. So now we have this computational method that allows us to study real materials, but the catch is that we have this mean field interactions that we know how to describe. This is kind of like a classical Coulomb interaction. And then there is the exchange correlation, which is all non-classical terms that we don't know exactly how to describe. And so we make approximations there, and sometimes they're good. I'll show you at times where they're good. When they're not, we go on to incorporate higher levels of theory. So we apply perturbation theory, and we include many body interactions. What I'll talk about is called the GWBSC approach. It's within first order perturbation theory. So I won't tell you the details of the methods, but I'll show you some results so you can see that it can be quite accurate. So okay. So just to summarize, so we apply density functional theory when we're interested mainly in ground state properties of the electron system and observables that derive from the ground state. And then for excited states, we apply either time-dependent density functional theory or many-body perturbation theory. So that's for electronic excitations. To describe atomic vibrations or phonons, this is, again, a really complex problem because we have, for n atoms, we have 3n directions of motion, and these 3n's vibrations or phonons will interact with every electron in the system, and so this can scale up exponentially. And so what we do is we have a classical description of phonons, and then we approximate their coupling to excited states. So taking these approximations, I just want to show you 3 examples where you can see that it's quite accurate. I think I can actually. So here I'm just showing bulk gallium nitride. And this is the imaginary part of the dielectric function. So we're looking at optical absorption. And so you can see this onset at 3.4. We know gallium nitride is a blue emitting material. It starts at 3.4. And then we even get all the way up here at the bright transition at 7 eV. In another case, this is work from the group of Stephen Louis in Berkeley. They looked at optical excitations in MOS2. And they can show really good agreement with experiments that's down here for the first few excitonic peaks in the monolayer MOS2. And lastly, when we incorporate this approximation for phonons, we can look at self-trapping of excitons, and we can look at compare the emission spectrum to photoluminescence, and we get pretty good agreement within 0.1 eV or so. So we can really reproduce the response of materials to electromagnetic fields pretty accurately. So now moving on to the two projects I'm going to tell you about. So I'll start with the first, which is the coherent phonon excitations. So we're interested in phase change materials. These are materials where we can change the crystal structure by applying an electric field, or in this case, by shining a terahertz electromagnetic field on it and causing phonons that will result in a phase change. So phase change is interesting from a device perspective because you can change the electronic properties of a material dynamically. So for example, here, this is showing going from crystalline to amorphous phase of a material. You can start to change its color. We can also get dynamically control microscopic properties. So we can shine a laser light. We can have a protocol where we have one laser pump and another one following it. And by manipulating the structure, we can basically tune not just the structure, but the electronics properties dynamically. So there's been work that shows you can have dynamic superconductivity, for example, and other really interesting physics that come out of this sort of dynamic manipulation of materials. So this is work that was done by my former student Anubhav and a collaborator at Argonne, Pierre Darance. And we really focus on what happens when we shine that terahertz light on the material. How does it couple to the electron density, and that excites a phonon, and that leads to a phase change. So we considered the Raman coupling only. So the Raman coupling, that photon interacts with the electron density, it polarizes that electron density, and it polarizes it in the direction of the phonon. And if we have a coherent phonon present, essentially, if that light can couple to the photon through this polarization strongly, then that phonon is going to be excited, and so we get a macroscopic phonon in the material. So this is the property that we want to calculate. So this is the polarizability. So we have the polarizability of the electrons, and then we have this coupling term. So the coupling of the polarizability to the phonons that are labeled Q here. So the red box here tells us the Raman coefficient, how strongly that electron density couples to the phonon. And then this Q is how much are those atoms actually moving. So that's going to impact how much the system as a whole changes its polarizability. So we have coherently time-dependent chi, or polarizability, or susceptibility, electron susceptibility. And so we get coherent changes in optical properties like reflection, absorption, so on. So here in our approach, we assume a adiabatic approximation. So that means we move the atoms and we assume the electrons follow. So we don't look at atoms impacting electrons impacting atoms back and forth. So that's part of that Born-Oppenheimer approximation, where we treat the atoms classically as independent from the electrons. We also assume that the phonon is a macroscopic quantity. So we ignore the quantum fluctuations associated with phonons and we treat it classically. So if we do that, Then we can describe the change in the susceptibility when the phonon is present, and we can build a quantum dynamic model based on basically a classical equation of motion for atomic motion, parameterized by quantum mechanical properties that we calculate. So I'm going to tell you about a couple of materials. So the first is tantalum disulfide. So this is a material that people are interested in because it displays kind of interesting physical properties. So if you shine a terahertz light on it, there's this oscillation that is called ringing, going between a high symmetry phase and a low symmetry phase in the crystal. And there's along with it comes a commensurate charge density wave that's on the macroscopic scale. So the symmetry broken in phase is the low energy state here. But if we drive a phonon, we can go between the high symmetry and low symmetry. And so we wanted to understand how do we sort of describe this behavior in a simple, physically intuitive way and kind of parameterize this interaction of the material with light. So this is how the way we went about it. We considered, so first of all, because the tantalum disulfide is metallic, we could approximate the density functional theory functional pretty well. And so we could stick within the DFT regime and not go to many body perturbation theory. So that helps us computationally. We also face the challenge of all of the normal modes, all of the directions of motion that are that this material can undergo. And so we really just focus on two normal modes rather than all of the possible phonons that could be present. And we looked at the modes that can take us from the high symmetry, high energy phase to the low symmetry, low energy phase, and then from one low symmetry phase to another. So these are called the Higgs and the Goldstone modes. So we have only these two to consider, and then we apply classical dynamics. We have a classical equation of motion, and this classical equation of motion, so it's force equals ma. So this is the ma part. This is the force, which is du dx. So as the atoms are moving, how is the electron density modified? And then we have that Raman coupling term, so that a force associated with that. And then we have a decay, just a damping term, because we know in reality, the oscillations will damp out eventually. And we take this term from experiment. So, here we have these parameters. We have U, the potential energy surface of electrons we calculate within density functional theory, and we have this Raman tensor that we calculate within time-dependent density functional theory. So here's the potential energy surface. The high symmetry phase is at this higher energy, about 50 MeV or so higher than the low energy phase. And the low symmetry and lower energy phase, there's 13 equivalent forms that form this kind of star as the atoms come together. So if we look at the same coordinates, but look at the dielectric response, we can see that, so this is the real part of the dielectric response. So we can see that in the high symmetry phase, it's a very large minus value, so it looks like a metal. In the low symmetry, it's a high positive value, so it looks like an insulator. So we're seeing this metal to insulator transition, a huge or a large change in the dielectric properties as we go between these phases. So why is there such a large change in the dielectric properties when we go between these phases? That's not because the atoms are moving very much. The atoms actually move very little as the system is undergoing this transition from high symmetry to low symmetry and back. But because the electrons couple very strongly to that really small motion of the atoms. And the reason for that is because this is an ionic system. So we have charges on the tantalum and charges on the sulfur. And so when that plus and minus move just a little bit apart, even zero point 0.3 angstrom, there's a really large response because there's a Coulomb interaction there, a Coulomb response. And so we get this huge change in the polarizability. Um, and so this kind of explained to us why this observation of this ringing occurs in the experiment. And then we put it into our equation of motion. We hit our material with a pulse, and we looked at how the phonons go, or the structure goes from high symmetry to low symmetry phase. And so you can see this ringing just like in experiment, and we actually put it against experiment, and it looks quite good. And if we Fourier transform from time to frequency, we can see a peak right here at about 2.5 terahertz in agreement with experiment. So the semi-classical approach seems to work for these phase change materials, at least in the case of being able to describe this oscillation of the structure. So the next thing we wanted to understand, though, is can we extend this to systems where you have anharmonicity? So anharmonicity is the case where the potential energy surface is not quadratic, so it's not doesn't look like a parabola, but it has other, it looks like some polynomial function. And so when that occurs at high photon intensity, so this is an experimental work. So you can see at low intensity, there's one peak associated with the coherent phonon at 3 terahertz. But as you go to higher intensity, there is a redshift of this peak. There's also mixing with a symmetry forbidden mode, which is the EG mode. So we focus on two materials that are really well studied to develop this model, bismuth and antimony, and this is data on bismuth. So this is they have this orthorhombic crystalline state. There's only 2 atoms in the unit cell, so it's pretty easy for us to study. And so we're going to look at the coherent excitation of this A1G mode, which is the one that should couple through Raman. And so we know there's an anharmonicity because we see this redshift or softening of the phonon mode. And we expect that there's going to be some behavior where if this is that omega 0 at 3 terahertz, there's going to be this delta omega, which is a function of displacement or photon intensity. So we developed this the semi-classical model further by not making an assumption of anharmonicity. So we can have a potential energy surface that's any order polynomial. I've shown just to the 4th order. And so now we just take that same equation of motion that I showed you, but now we kind of look at the anharmonic effects. But what we really want is to be able to provide, let's say, experimentalists ways to quantify anharmonic effects without doing a DFT calculation. So we wanted to see, can we make a simpler model that incorporates anharmonicity? And so I won't tell you all the details, but basically what we found is that we could take a piecewise linear approximation where at every point we can assume that we have on this potential energy surface, we assume that we have a linear potential energy surface. So let me tell you, so this is the actual potential energy surface. You see it curves out. It has, because of strong anharmonicity, as we go to higher and higher displacement of atoms. And this is a perfectly harmonic structure fit to that. And so you can see we can try to develop a little bit of anharmonicity with this, what we call piecewise linearity. And so we introduced this optimal linear approximation, and this was named by my student who really liked the snowman Olaf. So so yeah, he sort of made it fit into this. But essentially we try to optimize how we define this piecewise nonlinearity. And from there, so now we have this approximation that we have a Q squared dependence, but with a coefficient that depends on the displacement. And so when we take this Olaf approximation, then we can start to introduce protocols that people could use in experiment to control those coherent phonons. So for example, if we have two pulses, so we have one pulse that excites a coherent phonon, if we want the second pulse to stop that phonon, or if we wanted to enhance that phonon, we would, if we are in a harmonic approximation, we would take the frequency of the phonon, we would take its period, replicate it to constructively interfere with the original wave, and so we enhance it. Or if we want to stop it, we apply destructive interference by cutting that period in half. But if we have anharmonic effects, then this doesn't work because the frequency is constantly changing depending on the amplitude of the excitation or the intensity of light. And so we use this Olaf approach to approximate this separation period, including anharmonicity. And we see that we can, so in this case, we were working for destructive interference, so annihilating that coherent phonon. And so we showed that we can exactly annihilate it by timing the pulsing based on this approach. So this approach can be used as a guide for experimentalists who want to control coherent phonons and basically not have to do a full DFT calculation to understand exactly how. So I think I'm going to move on to the next project that I'm going to tell you about, where we're still looking at dynamics, but in this case, rather than classical dynamics like I showed you for phonons, we're looking at quantum dynamics. So in this case, we're interested in spin-coupled optical excitations in magnetic materials. So spin excitations are of interest because we can store information in spins. So whether it's a single spin or a spin wave or a magnon. And if we can store that information and it couples to an photon, it can couple to photon or electronic excitation, then we can read it using a photon. And in addition, when we have these low-dimensional materials with heavy atoms like the transition metal dichalcogenides, the interactions are stronger because we have low dimensions, and so we can have really strong optical and spin degrees of freedom coupling. So we started with Samir, who's right there. We started, to try and develop an approach to look at the quantum dynamics. So we worked on already available work within many body perturbation theory to look at optical excitations, and we incorporated what happens if we apply a magnetic field. So we want to apply the electric field to get optical excitations. In addition, we have a magnetic field that can push our spins around. So try and look at that coupling between the optical excitation or exciton and the spin wave. So we apply this to nickel phosphorus trisulfide, which is an antiferromagnetic insulator. And in the past few years, people have become really interested in this material because it was shown that there is a really sharp emission peak that's shown here. And if you look at the scale, you can see that it's in the MeVs in width. So it's very sharp at about 1.475 eV. And this peak shows Zeeman splitting. So it interacts with the magnetic field. And so it's, there's evidence that this state is a spin coupled to an exciton or optical excitation. The nature of what this state is, though, is really has been under debate because this is really hard to simulate. So we have to simulate the interaction of optical excitations with spins. We may even have to look at phonons as well, although I won't talk about that here. So there's work that suggests that this is a DD type of excitation, and it interacts with the magnetic field through spin flips. because of spin-orbit coupling, or a charge transfer type of excitation where there's a charge transfer from nickel to the sulfurs that it's bound to. And so the nature of the excitation will tell us about how localized it is and how we can manipulate it. So it's important for us to understand the nature of the excitation. So in this work, we want to take this quantum dynamic approach and try and understand about this excited state and how it couples to spins. So this is the emission. So you can see the sharp emission here. But there's also other experimental data that seems to a little bit contradict the emission. So for example, we have this ARPAS. So this is photoemission and also inverse photoemission that's momentum dependent. And from ARPAS, so for inverse photoemission, it was an alkali doped ARPAS measurement that allowed them to probe the conduction band. So the conduction band, there seems to be an agreement that it's a D nickel Ds. The valence band from 0 to 1 eV, there's very little signal. From -1 eV, so 1 eV below the valence band, it looks like a D type. And then at about 2.5 or so, it looks like an S dispersive band down here. So previously, we did some simulations within DFT to look at the nature of the bands. And we predicted like a mixed SP character in the valence band, a D character in the conduction band, and a D band that's way deep in the valence band. And so that told us that this level of theory was not enough. We have to go beyond it. But also, I would say this contradicts the idea that you have a DD transition because the D bands are 1 eV below the valence band, although it's not clear what the character of the bands 0 to -1 are. Looking at our predictions for the nature of the low energy bands, what we found was when we go beyond LDN, add many body corrections, we get D band coming up closer to that -1 eV that was seen in experiment, but not quite there, so about -2 eV. And this band consists of states that look very localized on the nickel. The valence band looks very much like delocalized over the sulfurs, P-type states, and then the conduction band looks again like nickel states. Given somewhat good agreement with many body perturbation theory, we moved on to look at optical excitations. Here's the optical broadband spectrum for this material. So we have some weak transitions at low energies and a stronger transition at about 2 eV and another one at like 3.5 or so eV. So that beta peak here is at the energy of that sharp emission peak. So in optical absorption, we see a pretty weak absorption that is at least in the same energy range as that very sharp emission peak. So there's, perhaps this is that peak, but somehow on emission, there's some interaction with spins that makes it very sharp and very bright. So in our calculation, so this is measurement, in our calculation, comparing with the experiment, we get pretty good qualitative and quantitative agreement here. Those smaller sort of weaker signals, we don't see them having any oscillator strength, but we do see states there. So we just see that they're symmetry forbidden. They don't couple to the photon. So we're going to focus on this peaks that are about 1.6 or so eV, which are about 1.5 eV in the measurement, which we think are associated with that sharp emission peak, and try to better understand it. So focusing on this, we first look at the spin expectation value. So does this excited state couple with spins? So when we excite, the electron or hole are going to flip spin, and so we get spin expectation value of 1. And so the lowest energy state, we see an expectation value a little over 1, which tells us that perhaps both the electron and the hole are flipping spin. And here we get something 1 or lower. So it tells us that this excited state is coupling to the spin degree of freedom. So there's spin flips happening as the electron is being excited. And we don't see that for the brighter states, only for these lower energy states. So looking at the character of the state, we see that it's localized around a nickel, but there's some sulfur character to it, but it's pretty localized at about 2.5 angstrom, which is not too different than the bond length here between the nickels and the sulfurs. And I want to know previous work that was based on dynamical mean field theory, so a Hubbard type model, have also suggested that this peak at 1.475, which was that bright or sharp emission peak, originates from spin flips. And our results are consistent with that finding. And we wanted to then look at, well, is this a spin wave that the electrons are coupling to, or just having a spin flip? So we looked at, so we applied our dynamics approach. So we kicked the system with a magnetic field and an electric field, and then we allowed it to run over time. So we kicked it, and then we went until we went to steady state. Then we took a Fourier transform, and you can see a strong magnetic susceptibility associated with that peak, that lowest energy peak at 1 eV, but none with that 1.6 eV that we believe is that sharp emission peak. So it tells us that this lower energy peak may be coupling to magnons, but not the one that we were interested in for emission. And this is just more evidence that there's so if we kick parallel to the spins of the nickel, we don't get any coupling to the magnons, but if we do perpendicular, we get coupling to the magnons, which we would expect if we have magnon interactions. So for that 1.6 EV peak, we see that there's spin flips, but we don't see this interaction with the spin waves, but this is still under investigation. So this is something that we're still trying to improve the calculations to try and understand it. So with that, I want to conclude. I hope that I convinced you that first principles theory can help us understand underlying physical mechanisms associated with excitations and also inform experiments. And in the future, maybe even we could use this to design devices and materials. So I just want to acknowledge my funding from DOE and Army Research Office and computer resources, especially the shared computing facility at BU, which is really great, and we can do so much because of it. And I should acknowledge my research group are sitting there mostly. So with that, I'll take your questions.
Yeah. Back a few slides where you were showing sort of a strip molecular diagram with that one here. And you said there's a localized state around a radius of 2.5 angstroms. What is the red? Because that red goes way further out than 2.5 angstroms. So what is that supposed to indicate? So
this is the electron density with given a hole, I think somewhere around the nickel, right? So on average, so if you go from top to bottom, you would expect like 5 angstroms, right? Because it's double the R average. I think it's about the same, isn't it? Yeah, because the sulfur is because you have sulfur, nickel, sulfur bond, so it's about 5 or so angstrom.
Okay.
The percentage of challenges on outside is not necessarily the same, right? Because it's an isosurface. Yeah. So we're only showing a percentage of it. If you And it's a bit more complicated because you can't, there's multiple positions. You have to sample around different nickel atoms, right? But we're in a relative coordinate system. So here, this is showing you if, for example, you were to sum up all the densities, but the holes are sitting separately, right? They're separate nickel atoms, but you can't take an expectation value like that because you're changing both hole and electron coordinates.
Okay.
So then we bring it back into the relative displacement coordinates. So you fix one.
I see. Okay.
So if in that calculation, some of that intensity there is not really actually there.
Yeah,
because,
no,
yeah,
it's an
so
artifact of your
yeah.
calculation. Okay,
it's
that's,
not an artifact.
well, it's,
The density there is the sum of all the individual calculations, but those are happening at different sites, right? But in an excitonic is going to form currently throughout the whole thing, but the sites, but the way we sample different atoms, correct? If you want to get an average expectation value, you would have to compute this with respect to by fixing one of the coordinates. That's why it's showing up as
in the
that.
center there. Yeah.
Yes, yes. So that's in the central coordinate, it's 2.5 angstroms. So on average, say, I only showed the expectation, I only showed the density of one of the nickel atoms, not all the ones that I've sampled here. Then the density will look much smaller. But the thing is, it's an antiferromagnetic system, so you can't really choose one nickel atom because there's spins that are aligned this way and spins that are aligned this way, right? So you have to sample throughout the whole thing. And but that was the density is more a visual thing.
Yeah, okay.
So just to tell the people on the Zoom, so essentially this equation is what we use to get the average. So we consider you know we need to basically think about the envelope function of the excited state. So we excite from somewhere and then the electron goes somewhere else, but where we excited from matters. And so in order to capture that, instead of, so normally we'd have to sort of integrate out one coordinate. So the hole where the electron came from, we might integrate it out and look at the electron density. But instead of integrating out, as Simon was saying, we just sample. So we sample a bunch of locations that are weighted by, how likely that hole is to be there. And so this comes from, a bunch of locations, but it's high probability locations. But this is just one position that's high probability that you're seeing. And, we choose an isosurface to make it, visually kind of consistent, but this number means something.
When you were talking about the coherent modes, the Raman, the first one you talked about, you selected 2 out of 117. How did you know which 2 to select?
So that was people who came before us, basically, proposed that, lots of people had studied the phonons, and so you could see that a certain phonon mode, so kind of like that A1G mode of the bismuth, but yeah. So there's one mode that basically takes you from, if you're at the high symmetry, you have one kind of distortion that takes you here, and then one distortion that takes you here. And so people had already mapped that out. So we could just take what was in the literature.
Slide just following this one, when you, was it this, maybe it's a couple more down, where you're comparing theory to experiment. So that one, right? You can see that, the orange and blue get out of phase pretty quickly. So how do you explain that?
So these are different excitation frequencies. So it kind of, yeah.
I read it. Okay, thanks.
Yeah, but we try to match the experiment to some extent.
similar work, but something akin to this with, I just wanted to kind of understand more of the approximations you're making, so I experimentally have studied systems where we did like, 5-6 atom molecules inducing like a hole in one of like a methyl halide series, that's a pretty popular one to study, like ultra fast electron hole migration. Typically with those, the timescales are like so fast, we're kind of ignoring any phonon type interaction because they're much slower than like the true electronic timescale that we're studying. Just want to understand you were talking about like emitters potentially, so I wanted to know if that's a step that you could take in the future to look at like as like looking at the timescales of emission, for example.
Yeah, so I think, I mean, that's something we're definitely interested in is looking at emission. So here, we're semi-classical, so we wouldn't really have a good description of emission. But if we stick with the quantum dynamics, so here we're looking at absorption. So we're allowing, we're hitting it with an electric field, we're hitting it with a magnetic field, and we're looking at the dynamics. If we wanted to look at emission, it would be the reverse process, right? So, so we would have to absorb, we'd have to allow phonons, because emission is a long time scale, whereas electronic excitation is femtoseconds rather than picoseconds, which are phonons, and then maybe microseconds even for emission, depending on the material and how long-lived their excited state is. And so we'd have to incorporate phonons, and then once phonons are present, then we'd have to incorporate an emission process. So if we wanted to do the full, absorption to emission, that would be quite complicated. So what we did in the work that I showed you, which was a static work looking at self-trapping, we just incorporated phonons classically, and then we looked at absorption, knowing that it's actually emission because phonons have already come into play, but not in our excited state calculation. So we could do something like that, where we incorporate the phonons before we start our dynamics, and then we incorporate kind of the processes that are associated with emission as we run the dynamics. So that's probably the easiest way to do it. But yeah, we're definitely interested in emission as well.
Being on Zoom, you see any in the chat?
Any questions on Zoom?
Yeah. Okay. None in the chat. Okay. Well, I think that's all right.
Okay, thank you. Okay, bye on
I wanted to
Zoom.
make actually one more announcement
Oh.
just before I end. Just to announce the next talk is going to be on April 16th. And we'll send an email about that. But this will actually not be at BU. So I just wanted to give a notice. So April 16th for people, we'll send out a notice when that talk is. So, all right. Thank you again for coming, everyone.
Yeah, thanks.
Thank you.